Okay, great. So the recording is on, so we can officially start. So good afternoon, everyone. On behalf of the DNS4EU Consortium, I would like to welcome you to the very first DNS4EU Stakeholder Group Conference. My name is Magdalena. I am a marketing manager at Whalebone, and I will be the host of today's session. Regarding today's agenda, as you all know, it'll be all about the DNS4EU. We will cover different angles, and I am very happy that I have here 4 speakers. All of them are experts, and they will share their insights and their expertise with us. And as you can see, the topics, we will start with the threat intelligence, then we will move to the protective DNS for governments, then we will touch the analysis of competing public resolvers, and we will finish strong with the DOS protection. Regarding the Q&A, it's planned at the very end of this conference. However, I encourage you to use chat on the right side, and feel free to address your questions directly to the speakers, and we will try to cover them either during this session, or we will come back to you via email later on. So I guess that's it, and we can welcome the very first speaker. So for those of you who check the agenda, this session was originally planned for Martin Stahlik, the threat intelligence lead at Whalebone. However, due to medical reasons, Martin is not able to attend. However, I'm happy that in his place I got here Mr. Viliam Peli, threat intelligence specialist at Whalebone, who will guide you through the first session. Just briefly, a few words about Viliam. Viliam is experienced and enthusiastic cybersecurity specialist, and his main focus is threat intelligence. He recently attended the Cyber Threat Intelligence Conference in Brussels, organized by ENISA, where he presented the threat intel research. So, William, thank you very much for finding time in your busy schedule, and the floor is yours.
Thank you, Magda, for your introduction. So today I will cover the topic of how we are shielding the Europe, how we are leveraging and using certain insights for advanced threat intelligence. So first of all, I want to tell you some statements, some actual facts. In 2020, NSA Director Anna Neuberger stated that 92% of current malware is using DNS, networking layer. And the IDC annual report currently states that 90% of asked companies had a DNS attack in their company during the year. So this is where the European Union project DNS4EU comes, which is trying to solve and create safe, stable, and private internet for the Europe. The project is an initiative by European Commission with the goal of providing private, safe, and independent DNS resolution for EU citizens, governments, institutions. DNS4EU aligns with the European Union vision of digital independence by providing alternative to the existing public DNS services, usually offered by non-EU tech companies. And also what makes us different is that the data stay within European Union under EU law regulations, and we ensure the privacy so the data are not misused. So who is actually in the DNS4EU consortium? The project leader is company Whalebone, and the members are from different countries and from different fields. We have in the consortium, for example, TLD registrator, universities, cybersecurity agencies, law companies, IT companies, and banking sectors. So how we actually do the threat intelligence? What is the purpose? How are we trying to protect the people? Well, the main pillar of the whole project is threat intelligence exchange. How we do it is the current challenge that CERTs have in their countries is whenever they find a new threat, it takes them hours to tell it to public, and also whenever you tell any person or anyone 100 times, do not click on this link, do not do this, eventually they will do it because we are humans. So how we do it is whenever, oh, okay, thank you. whenever a CERT finds any such threat, they immediately report it to us, and we propagate it to the DNS4EU resolver in real time. So the end customer, or let's say in this statement, let's say the EU citizens are immediately protected when they are connected to the resolver. So the whole goal of this project is to protect the Europe from regional and global threats. So how do we actually do the TI? It's not only that we get threat intelligence from other CERTs. We are combining our in-house research that we do with data from external partnership. One of them are CERTs, and other antivirus vendors and cybersecurity research vendors. Then we take those data, we put it into our machines that are evaluating them. They're categorizing them, evaluating them, giving them the score if they are the actual threat, if they still are malicious. For that, we have multiple machine learning models. We use historical analysis and statistics, and also other metrics for the analysis. And after we evaluate the domain is actually malicious, we propagate it to the resolver, so it's immediately blocked. Not only that, we still retrospectively do the analysis all the time. So we actually remove the malicious content after it's not actually malicious. And we also take the feedback from the endpoint users. So how does it look like? The certs from different countries are giving us their intelligence, their threats. It goes immediately to the DNS4EU project. And how are we actually doing this? Well, for this, we have a tool which is called MISP. It's open source threat intelligence sharing platform created and maintained by Luxembourg CERT, Circle. So whenever you have a MISP, you can create your own MISP and create forward threat intelligence data about malicious domains, IP addresses, files, or anything else. Usually, CERTs and national CERTs are using their own instance, and they connect to each other or contribute to the community. For example, as you can see on the screenshot, we have example of such shared data that was given to us, and you can see that not only domains are sent, but also IP addresses and others. What is great about MISP that it allows you to categorize, create your own tags, give the context, which is in most cases very useful for the processing of such domain and to evaluate it. And what is also great is that even if you are not directly connected to such MISP of other CERT. Some CERTs even give the data to the community or publicly. So if you are connected with other CERT that is connected with such MISP, they can also give you their data that was shared to them. So what have been done so far? We are still trying to connect with and connect to our MISP as many CERTs and cybersecurity vendors as we can. And currently, we have 430,000 items in our MISP. And these include domain names, attachments, IP addresses, files, screenshots, and many more. So what do we do with them? Actually, the first thing we do is the reception stage. We will get the data, the categorization, the tags, everything they can give us. Then we are categorizing them. We are giving it and we are putting it into our machine learning models for the evaluation. We are analyzing all the data that was provided to us. We put the score into it and then we put it straight into the resolver to block it. In more depth, we had around 5,000 attachments so far, 90,000 IP addresses, 50,000 hashes, multiple file names and email sources. And from those, 300,000 malicious domains were immediately blocked that we got. I talked about this before. Out of it, half of it was used from a remote set MISPs that we are not yet connected with, but they were propagated to us from other CERTs that we are already connected. So I also have some showcase of items that were shared with us in the MISP. For example, from Romanian CERT, we got a ransomware attack, which was, as you might have heard, this year was part of Blockbuster ransomware. And it was immediately blocked by our machines and propagated immediately to the resolver, so the end citizens can be safe. We also got multiple phishing campaigns we have seen this year. For example, from Ireland, Estonia, and Poland. They were mostly using JavaScript credentials harvesters. And I'm going to tell you more about the Poland one, which was OLX. OLX is actually something like Craigslist in America. It's a marketplace where people buy and sell anything that they want or do not want. And this year, CERT Poland have seen multiple phishing campaigns in the region, targeting OLX. So basically, the threat actors were creating duplicates or replicating the actual OLX marketplace, and were putting phishing kits into them to target the Polish victims. The OLX PL was even in the domains, and many people might not have seen it on their website that they are actually not on the correct OLX domain, and they had really it was usually on the second level of domain, so it was visible for the citizens. And during this year, we have seen two biggest events. First one was during January. It was after the Christmas, the holidays. People or the victims were trying to buy and sell stuff they got from Christmas, and we have seen multiple or the biggest phishing domains during that year. And the second was during February, close to Valentine's Day. And during that time, people usually buy stuff for their loved ones or selling if in case they broke up before the Valentine's Day. And what we have seen, well, out of that, we have seen 2,531 unique domains that were blocked, and thanks to Poland CERT. And we have seen from our logs 2,100 attempts to access these sites. And to this day, still out of those 2,500, there are still thousands of them blocked or still active, but all of them are blocked. But out of them, thousands are still active. Well, thanks to that, we were able to immediately block all these sites to prevent from frauds. And what was also, after we were checking the websites, we have seen that they were really close to the actual real OLX marketplace sites, and they had the phishing kit whenever you try to log in or put anything into the website. But the second thing was they even put a QR code, which was also a phishing QR code that whenever you scanned it, it would redirect you to their other phishing sites. So they had to make sure twice that they would fish you. And that would be it from my side. If you would be interested in the project DNS4EU, you can find it on joindns4eu.eu. And in case you want to discuss Safer Europe with me, feel free to scan this QR code, which is definitely not a phishing, or you can just straight connect with me on LinkedIn. And even if I wouldn't be able to answer your questions today, you can still hit me on the email address or my LinkedIn, and we can talk about it. Thank you so much.
Okay, great. Thank you, Viliam, very much for your insights. I was asked to include threat intelligence topic in this conference, so I hope that the attendees are happy for the results that we have. And you are on time, so we have like 1 more minute, and there are actually 2 questions in the chat that relate to you. So I'm wondering if we can briefly cover them and then move to the next topic, if it's okay with you.
Not a problem. Let me find the questions.
Okay, so
can you read them?
Yeah, the first question is from Craig. So what sort of validation is done on the IOCs provided by the CERT? How do you ensure this will not cause a false positive? URLs cannot be deployed on DNS.
Yes, exactly. You're correct, Greg. As I mentioned in this slide, the first thing that we do, we try to get as much data about the website or anything that they give us, even their URLs. Then we process them, so they are converted to domains. We categorize them, and using our machine learning models and other metrics, we try to assign them a score which prevents putting false positive into the resolver.
Okay.
Hope that answers your question.
Great. Let us know, Greg, if there are any further comments. And the second question is from Andreas. It seems only a few certs report to you. Is it envisioned to extend the number for certs reporting to you to improve quality of regional blocking of threats?
Yes. From the report I showed you, I have only included a few of them, but we are connected with multiple certs currently, and we are actively working on connecting with more and more certs as we can. And in this time, we have multiple even signed POCs with them, so they would join us.
Okay, great. William, thanks a lot for your answers. We have more questions in the chat, but we will cover it later on so that we can move to next topic. So thank you for your questions. We're happy for
Thank
that.
you.
Okay, so we can move to the next topic. So I would like to welcome Michal Havelka. He is product manager at Whalebone, and he focuses mainly on ISPs, corporate and governmental segment. And Michal is also experienced cybersec guy who attends many events and led many tech talks. So I'm happy that he will guide us through a very relevant topic, and he will talk about the productive DNS for governments. So Michal, floor is yours. Thanks for joining us.
Okay, thank you, Magda. Thanks again. Can you confirm that you can see me, hear me, and see the slides? Just to be sure, there's no glitch.
Yes, we can see you, hear you, and we can see the slides.
Okay, lovely. So just to repeat, yeah, I'm product manager responsible for technological and product part of the DNS4EU project, with great support of my colleagues, not just from Whalebone, but also from other consortium members like Peter here, yeah, who is responsible mainly for security and encryption part, and also Vladimir, who's developer of the net resolver we use for this project. Yeah, but today I want to talk of what is happening actually on the government field, yeah, and how the project and the DNS4EU and the development we are doing, yeah, how we will support them, yeah, with their initiatives to actually protect the state's institutions, yeah. So first of all, we need to understand what is happening now around the world, yeah. So there is let's say product, yeah, we call it DNS4Gov, which translates to ability to protect hundreds of organizations. This is already happening around the world, yeah. They launch these protective DNS services in 4 states, as far as we know. That was Australia, Canada, UK, USA. They're usually leveraging the existing products on the market, yeah, and offer it as a free of charge national service to the state organizations. Yeah, they launched this service. Service, let's say, from 2017, 2020. So it's under pressure, or it's running already, and offered, and the hundreds of organizations are already protected, millions of requests being blocked. What is happening also now, they are trying to touch also other organizations, not just the state ones or governmental ones, but also ISPs, and offer the service to them, other commercial subjects like normal companies, enterprises, and offer the service to them. But how it started, it's always with the intention to protect the government, the state organizations. I want to talk about the multi-tenancy or advanced multi-tenancy, and how we want to support the governmental organizations, and especially national cybersecurity agencies providing the services. Is there a glitch in the presentation, Magda?
No, I guess that it stopped sharing. So if you can share it again.
Okay.
Let's try.
Okay, let's try it again. Okay, lovely. Yeah, what I wanted to say, the national protective DNS service is run by different organizations. It can be national CERT, it can be cybersecurity agency, it can be Ministry of Defense, Ministry of Interior. It differs, yeah. But I will usually call them as national cybersecurity agency, or national CERT. Yeah, but it can be also a different organization. So to understand how they run the service, we need to explain, let's say, the launch phases. Yeah? Someone can call it the maturity levels, yeah, how mature they are, but it's more connected actually to the time rather than to the maturity. Yeah. So in phase one, agency or the national CERT search for simplicity, easy deployment, and scalability. So they're able to deploy to hundreds of organizations. How they do it? Yeah, they launch the national cloud resolver, or to be precise, set of resolvers, and start with the evangelization. Yeah. Sometimes they force, especially the critical infrastructure services, but usually they encourage the organizations to actually join this protective service and be protected. So what features and the requirements they have, or features they are seeking for? Of course, it's advanced protection. Yeah, this is something what as Whalebone we already do offer to dozens of big telco operators, to hundreds of ISPs. So we are pretty experienced in this one. So this is covered. They search for simple deployment. Yeah, it really needs to be simple, especially for the small organizations. Yeah, but it is simple actually, because they just redirect the endpoints or for example, the edge router to the new DNS resolver, to the protective one, the national one, and they automatically get the protection. Yeah. So the biggest work here is in evangelization and how to actually involve as many organizations as possible. Yeah, they search for easy scalability. That means deploying of hundreds of or thousands of organizations in a short time, which is easy. Yeah, if they just redirect the DNS traffic. And they search for regional threat intelligence. Yeah, I think Viliam very nicely actually explained how the threats are catched. It's not just phishing; it can be also a malware which is trending in the country or in some segment. And they are able to propagate this information not just via MISP, but also leveraging other options like RPZs directly on the resolver or denial lists on the DNS4EU backend. It really depends what they require, if they want to share these IOCs with others or not. And so this is phase one. This is how the deployment usually looks like. Yeah, there is a set of organizations. They can be smaller ones, bigger ones like schools, small municipalities, county offices, and they redirect the traffic. They redirect the traffic to the national DNS resolver, and from there, the data are flowing into the DNS4EU cloud backend. And this is simple as that. Yeah, but as times go, they reach phase two. And the organizations within the state start to be more demanding in terms of traffic visibility, analysis, management. They want to integrate with their current solutions they have. Um, they want to define their security or content policy. And the answer on this is to deploy their on-prem resolvers within the organizations. Yeah, so what they require in phase two as state organizations? They require network insights, yeah, the ability to see the DNS traffic, the threats, but also maybe content events. And so they are able to reveal and focus on the trending threats and how to prevent them, and especially on most threatened devices and how to protect those or focus on those and what to do with them. So it's not just protection; it's also analysis. They also require content filtering, especially popular with universities, schools, and other state organizations to block like peer-to-peer networks, adult content, gambling, and so on and so forth. Yeah, to a certain extent, it's also possible in phase one, but any fine-tuning and it's really possible only with the on-prem resolver. If it's a bigger organizations like a big municipality or some I don't know, critical infrastructure like electricity company, they also need to integrate with their current solutions. Yeah? Like for example, if they use any CM, security event management system, they want to send those logs and events to their system, so they are able to validate or or analyze them from not just from the DNS protective service, but also from other security services. They want to integrate with their Active Directory to see not just the IP addresses, but also the host names of the devices for faster analysis, integration with their local domains, and so on, so forth. And last but not least, they also want to protect not just the devices within the network, but also the devices which are in the organization, but they work outside of the network. So support for roaming clients, to be able to protect them out of the network as well. So these are typical requirements of phase 2. Of course, we support all of them. And this is how the deployment schema looks like. Smaller organizations usually remained redirected to the national DNS resolvers and get the basic protection. But the more demanding organizations like hospital, electricity providers, or maybe even capital city municipality, they want to deploy their own on-premise resolvers and get all those additional features which they require. So that was phase 2. And the most advanced scenario is in phase 3. The national CERT realized need for global, national, or even segment insights, advanced multi-tenant analysis, multi-tenant, I mean multi-organizational analysis and management. And they are also start to be very demanding on the security of the collected data. So what they require? They require global dashboards, so they are able to analyze spikes and anomalies in threats across the organizations, across the multiple of them. They require advanced multi-tenancy, which means to quickly create and deploy new organizations, which supports the threats and traffic visibility within the organization. They want to apply one policy and inherit it to all of the organizations within the tree structure, which is below. I will show you on the demo in a moment. They also require some risk scoring. They want to see actually how threatened the organization is. If they should focus on them, if they should provide them with some support, with some specialists, with some management, or if their DNS traffic and threats seems pretty normal, and they do not have to put that much focus on them. And again, last but not least, they also require dedicated backend to collect the data within their infrastructure. On the last slide, we always use DNS4EU backend, which is running in the DNS4EU infrastructure. But the most demanding governments or security agency demands their own dedicated national backend, which is also possible to deploy and redirect all the data to their backend managed by them. On this slide, this is let's say the most advanced deployment schema. Again, the smaller organizations like schools, town halls, they are using national DNS resolvers for standard protection, but no insights into the network. Then we have another organization using standard on-premise DNS resolver. And the most advanced scenario is Ministry, for example, of Home Affairs, who actually manages more organizations within their structure, like police forces, fire and rescue services. There can be more of them. So these data are collected, let's say, in the tree structure. And these, let's say, sub-organizations can use one shared DNS resolver and again send the data to the dedicated national backend. So this is the most advanced scenario, what we see, what we observe, what are requirements from the governments, and how we want to support them to achieve their goals. Now let's have a quick demo. I presented many features, but I picked one of it, which is tenant management and policy inheritance, and how it actually looks in the administration console. So hopefully it will work. So now here you can see the video and insight into the administration portal. And here you can see the tree structure of the organizations within the state. On the top, there is the provider, the National Cybersecurity Agency. And because I'm from the Czech Republic, I picked the Czech Republic as an example because I know the country very well. And the Czech Republic is divided to the 14 counties. There's like 3 of them, and the counties manages different kind of organizations like hospitals, municipalities, schools, and so on and so forth. Yeah, so if you are, for example, administrator, whether it is like of the particular county or national cybersecurity agency, depends on the permissions, you can easily create just a new organization, clicking add here. Fill the organization name. This time it will be a small town, Hodonín, actually in the Czech Republic, and you can create organization for their municipality. Later, you may find out that you actually created in the wrong country, so you just easily move it to the correct level within the tree structure, which in this case will be County Jihomoravský, which is our county, and under municipalities. So now we can see that the Hodonín is moved to the correct level within the tree structure. So now let's check the access rights or permissions, how it is divided. Right now, it just opens the county Jihomoravský, which is one of the counties here in the Czech Republic. And here we can see, sorry, it just jumped. Yeah, and here you can see our friend, the national cybersecurity analyst called John Doe, who is assigned actually to this county to help the organization, with the analysis, with the security support. So this John Doe, he has a role. Yeah, his role is a viewer here, so he cannot actually configure or manage anything, but he can see the data of the particular organizations below his organization, below his node within the tree structure. Yeah, we can check his role, and as you can see, we have like 4 roles: owner, administrator who can manage the organization, viewer who can see the data, and granular roles hidden under the specific. So the John Doe is viewer, and we can see that this role is actually applied also for the sub-organizations. So we can apply those role here. We were on the level of County Jihomoravský, and now we can check the particular organization, which is Brno municipality, the city I'm coming from. And if you can check the users, we can see here there's also John Doe, and he is a viewer. Yeah, he's external user because he was defined in the different organizations, but he has a viewer right in the Brno municipality organization. So he can actually see the data and help them with some management or analysis of what is actually happening within their network. What we will show furthermore is policy inheritance. So now what you can see is the configuration of the security policy. And you can configure different things here. For example, how strict you want to be in terms of blocking. And that means like which risk score assigned to the domain will be blocked or not. You can define your own allow or deny list. And also specify the content filtering. Yeah, so this is the policy for schools. Yeah, so there's some specific deny list applied only for schools, and also some typical content filtering, which is set up for schools like adult, crime, crypto mining, peer-to-peer network, of course, and also some entertainment, like social networks and games, because these are really only school networks. So we hit the save, and here on the right side, there is this magic button called policy scope. And this, if we tick it or turn it on, we will make the policy also available for the sub-organizations within the tree. Yeah? This policy then can be enforced or only recommended. So we can check it now. Yeah? So we define this policy on the schools level. And if we check it on the gymnasium in Hodonín, which is one of the schools within the county, we can see the policy is automatically inherited to this organization that is defined by the parent company. And we can see all the settings which we set on the upper level is automatically inherited here and can be applied, recommended, or enforced on this level. Now we can quickly demonstrate how the inheritance works. For example, we decide to not block the chat domains, and we can decide to be a little bit stricter or more strict on what we block in schools, and save it. And if we check on the level below, the changes are automatically propagated here. Okay, so that was a quick demonstration, quick demo, how this advanced multi-tenant management in the tree structure works, how the policy inheritance works, and of course, with this tree structure, you can share or share the data across the organization, check the shared dashboards, and so on, so forth. So that was my demonstration of the tenant management and policy inheritance. If you have any questions, I'm super happy to answer them in chat. And if you're actually interested, for example, you are from some government organization and you want to actually see it live in your country, I strongly recommend to contact my colleague George Buhaj, who is government liaison, and he's in contact with basically almost all the governments or governmental organizations around Europe. And my name is Michal Havelka. So thanks again for listening. I would be super happy for your feedback, for your questions, and I will be happy to answer them.
Okay, great. Thanks a lot, Michal, for your presentation. I'm glad that you showed the demo and all the details. There is quite a few questions in the chat. However, I will give you some time to go through it, as some questions are complex, and we can get back to them either via chat or later on in the Q&A section, if it's okay. But thanks a lot for the discussion. It's great to see that you're interested in all the topics, and we will be happy to answer your questions. So now we can move to the third topic. We will move to different area, because our next speaker is Peter Thomassen, CDO of DSEC, who will present feature analysis of competing public resolvers. And it's a great topic. I'm looking forward to Peter's presentation. Few words about Peter. Peter is founder and CTO of DSEC. It's a free managed DNSSEC hosting platform that is focused on enhancing the security of online data transmission. And he works on internet architecture security. And I would like to welcome Peter to the stage. Peter, floor is yours.
Hello, thank you. Thank you for the introduction. I'll tell you some about the features that DNS4EU has from a technical perspective as far as the DNS resolution service is concerned. So we're not talking now about protective features. We're talking about DNS resolution reliability and such things. All right. So as Magda mentioned, DSEC is a member of the DNS4EU consortium. And I represent the DSEC. We are a not-for-profit organization that works on standardization of DNS security stuff, mainly in the context of automating it better, because it is sometimes hard to use. And we also show that these standards actually, or automation techniques actually work in practice by using them in our own DNS hosting platform. That's free, so it's like Let's Encrypt, but not for certificates, it's for DNSSEC. And it's all automatic. We have a nice API and graphical user interface. We support modern things like DANE, which is for identity management through the DNS, and some other things. And we have 15 locations globally for low latency. We started in April 2020 and have about 50,000 zones now that we host, so domains more or less, and serve about 10 billion queries per month. And November last year, when I gave a similar presentation, it was only 4 billion. So it's actually moving quickly. I'm also a member of the ICANN Security and Stability Advisory Committee, which advises on security of top-level domains and IP addresses. All right, so in DNS4EU, we focus mainly on security and privacy issues of resolution and how the data is protected in terms of privacy for the user, and that's where we take it from here. So the DNS4EU resolver has a policy that I guess will also be published once it goes into operation, and it says essentially that it's designed for privacy through data minimization when processing DNS requests. So no data is collected and stored unless that's necessary for the proper functioning of the resolver and the debugging. And if anything is collected for these purposes, that is the domain name and the query type, which is, for example, whether the question is about an IP address or whether it is for an email server name or something. The response is also stored, which is a public piece of information anyway. The point in time when that happened is stored. The resolver identifier is stored because there might be multiple instances. And the so-called client ASN, which says where in the internet the request came from. That's like a group of IP addresses. Yeah, so that stuff is used when there is like very high load or bottlenecks and stuff to figure out what the reasons for that are and to manage the service. Not all the queries are logged. What's logged is 5%, and everything else is discarded right after answering. Other resolver operators do that too. We'll get to a table later to see that. And they use different percentages, but that's what we will start with. Also, the data is deleted after a maximum of 6 months. And after that, we might keep statistics. For example, how does the number of queries evolve throughout the time of the day, or how does the number of queries relate to a country, but nothing that is particular to any particular queries. So there's no record for each query after that. Also, no information, especially no PII, IP addresses or other identifiers are transferred or sold or otherwise retained unless that's required by law, when there is, for example, some prosecution order or something. And no data is combined with any other data that could identify end users. In addition, no blocking is done except when that's required by law or when the user requests it, as was discussed in the earlier presentations for the various blocking variants of the resolver. There's also a non-block variant for the public resolver. So about security of DNS responses, how can DNS manipulations be prevented? A technology has been developed about 15 years ago or 20 years ago. It's called DNSSEC, and it allows a domain owner to include digital signatures with its DNS responses. So for example, if you go to whatever DNS4EU website, I don't know if it currently is the case, but depending on the DNS operator of that domain name, digital signatures might be present, and the resolver receiving such responses might then be able to validate those signatures. And that prevents what's called DNS cache poisoning. So in general, DNS responses are stored in the cache of the resolver because another user could ask the same question soon after. Let's say after 10 minutes, a different visitor comes, and then the resolver can use information from the cache. But if somebody else managed to convince the resolver to accept a fake response, it will also put it in the cache, and then all the other users will also be affected. And so DNSSEC, signature validation, prevents that if the domain name uses it. And it also not only prevents like random things, like people in Wi-Fi's, for example, messing with DNS responses, it also prevents certain criminal acts or acts by state-sponsored attackers. It also makes other attacks less attractive. So one notable case, for example, is a routing attack on Amazon's DNS service, which is called Route 53. Back in, I think, 2000, when was it? 18. The website of a crypto coin exchange platform was hacked, not directly, but instead the IP routing was changed for the DNS queries that went to Amazon, because that's what the website used. And the attackers managed to divert all the DNS traffic for the website to themselves. And then they sent fake responses, and then they set up a fake website, and they managed to divert some Bitcoin money. And if that page had used DNSSEC, then it would not have prevented the diversion of the DNS traffic, but the fake name server would not have been able to present the correct signatures and would have been detected. And also DNSSEC is hoped to be the technical foundation for some future trust applications. It's not very widely adopted yet, but so for example, there is something called DANE, which is for email server authentication and other purposes, but it's used for about 4 million email domains today. And there's other concepts like digital trust registries that could be used for global ID card checks and other future utopia, things like that. So that's a DNSSEC primer essentially. And I brought that up because I'm now going to talk about the DNS4EU security requirements, which are in a document that says what are the features that will be supported from a security perspective, and DNSSEC is one of those features. And there is some technical stuff which I will spare you, different algorithms and such things, but DNS4EU is going to support that. Another mitigation that will be supported for similar attacks is to randomize some fields of the data packets that get sent. The reason for that is that an attacker, in many cases, at least for certain types of attacks, would have to be able to predict those random numbers that occur in the data packets, because they have to be copied into the response. So when the attacker didn't see the question and the response has to kind of echo back the same randomness, then it's harder for an attacker to make that match. That's why we support these things. Then DNS usually works over UDP. That's a transport mechanism in the internet that is very simple and very fast. So there is no connection setup. It's just one packet with a question, and then the response gets sent to whatever the source IP address on the packet is. It's like on a postcard, whatever the sender says, but it could be fake. So you could be asking a question and the response, you fake the sender of it in the packet, and then the response gets sent to your neighbor or something, and you want to attack your neighbor. So you ask questions that cause very large responses, and then your neighbor will be swamped by all the additional traffic. So it's called an amplification attack. And because UDP is prone to this kind of attack, there is a limit of 1400 bytes for responses, and if the response is larger, we will not deliver it and instead switch to another transport mechanism, which is called TCP and does not have this weakness. I'm explaining it because it's interesting in the feature we support, but I also have to say it's very standard and pretty much everybody supports it. Then I mentioned earlier that DNS responses are stored in the resolver's cache for a certain time. Now the question is, what's that time? That's also specified in each response. So some responses might be stored for long, some responses might be stored for short, but not every value makes sense, because if it's too short, then actually the cache is not really useful. Like 1 second is not a useful storage time. And also 5 years is not a useful storage time, because if you want to change the information, you have to make sure that the information actually is removed from the cache at some point. So we cap the TTL, which is that time to live, on both ends, low and high cap. Then in case of misconfigurations, which sometimes happen, it's possible that information is in the DNS resolver cache that the domain owner does not like or wants to change quickly because they made a mistake. So in that case, it's possible to go to the DNS4EU website or some API and request the cache to be purged for that particular domain name. That's also supported, for example, by Cloudflare and by Google public resolvers. So it's a good feature to have. And back in the day when the feature didn't exist, people would be like emailing around DNS resolver operators and trying to get it done manually, and it's much better if there is an interface for that. Then there is a privacy technology called QName minimization, which protects, under certain circumstances, the subdomains of the domain that you're asking for. So DNS resolution involves a number of actors because it's hierarchical. There's the top-level domain and the national registry and all of those parties. Not everybody has to know what the subdomain is, and QName minimization takes care of that. And then there is transport security. So this is now about encryption. Usually DNS is clear text, even if it is signed. A signature is not the same thing as encryption. Now we're talking about encryption. If the resolver talks to the name server of whatever the domain is that is asked for, if that name server says, I support encryption, then DNS4EU will try to use encryption for that connection, so that when somebody is listening on the connection, it will not be very useful to the attacker. And so that's upstream, that's kind of on the backside of the resolver from the user's perspective. But if the client, the front side, the user wants to use encryption, we are planning to offer that as well. It's called DNS over QUIC. There's other ways to do that too, but we think QUIC is the way to go. And that's a feature that is pretty new. It's been developed in the last years. Not generally supported yet by the competition, but there's at least one competing vendor that does support it. And then there's also something that's called DNS over HTTPS that is useful when a website wants to make a DNS query through JavaScript. That's not technically necessary for a DNS resolver to support. If it is not supported, then it will still work, just not for JavaScript, but that's not really an expectation. But it's a nice to have. So the requirements document lists it as a recommendation. All right, so here we are with the comparison table. I think some of you might have seen this before, but it's been updated. So it's not exactly the same as before, it's a little more accurate. On the left-hand side, in the first column, some of the features that I mentioned are listed. If you have questions about that, you can ask in the chat or later. I will try to not be too technical, but I think I've explained most of it. And the second column has the attributes for DNSSEC relating to those features. And then there's the Google Public Resolver, Cloudflare Resolver, Quad9 Resolver, and AdGuard, which is a privacy-aware resolver operator. And that's the one that has, for example, DNS over QUIC encryption connections that I mentioned earlier. I also said Google and Cloudflare have cache flashing capabilities, while Quad9 doesn't offer that, and AdGuard also doesn't. Everybody essentially supports DNSSEC. There's different signing mechanisms, and not all of them are supported by everyone. But one also has to say that the first two ones here are the main ones that are being used. So the other ones are more like an extra thing. You can also see the log sampling rate at Google and Cloudflare, and Quad9 is lower. So I mentioned before we will start out with 5%. The reason for that is that initially there will not be much volume. And to do any reasonable debugging, it's important to have some meaningful absolute numbers. So that's why 5%. My personal view is that this number could soon be lowered after the service has been reasonably adopted. Then about IP address location, I mentioned earlier the client ASN, which is an IP address group, will be stored in the logs. That's not what others do. So for example, Google, Cloudflare, and Quad9 have either geolocation, which tries to figure out what is the geographic region for a given user IP address. And Google, for example, wants to do that with an accuracy of 1,000 users geographical point, and Quad9 with 10,000. There's databases for mapping IP addresses to GPS coordinates, kind of. I mean, it's not very accurate, but more or less you can think of it like that. And Cloudflare doesn't do that. Cloudflare instead stores the IP address, but they throw away the last part of it to make it pseudo-anonymous, more or less. And then as a final comparison feature, each of these providers, except for Google, offers their resolution service in various flavors with extra filters. And so this one lists which supports which. Everybody supports an unfiltered version, which is U. And that's the only thing that Google supports. And the others all support, including DNS4EU, a protected service, which is with blocked domains for malware and phishing and such. Then I think it has not been completely decided whether DNS4EU in the public service, not the DNS4Gov, will have an adult content blocked or ads blocked variant. But for example, Cloudflare has that. And there's currently no intention to do filtering based on copyright infringement. And also nobody else does that except for Quad 9 because they have been forced by a court order. So obviously when there's a court order, you have to comply. All right, so that's almost it. I will have one more slide on future stuff, and it's not meant as buzzwordy as it sounds, but one or two of you might have heard about the fact that a new type of computers is being developed, quantum computers, and when they arrive in 10 years or 20, nobody knows, it is expected that the current encryption and signature mechanisms will not be secure anymore. So I'm not saying the quantum threat is immediate, and I'm also not saying we're doing quantum computing. That's none of that. I'm just saying that the internet will have to transition to more secure stuff by that time. So for encryption, some standardization work actually is going on, and the first algorithms have been standardized this summer. And then for signing, which is what DNSSEC is about, some algorithms are candidates that are in the standardization process. And so DNSSEC will have to transition to one of those or another one eventually. And the interesting thing regarding DNS reliability is that the signatures of those new algorithms are much larger than the old ones. And that's not a problem in terms of bandwidth or internet connectivity speed, but it's a problem relating to the 1400 byte limit I mentioned earlier for UDP connections and amplification attacks and such things. And it turns out some resolvers get confused for this, and then they drop responses, and then the client waits forever and times out and there's an error. So that's what you want to avoid. And we did some measurements and actually found that if these signatures are used, I'm not saying they would work everywhere, but if DNS4EU is used, then that would not impact reliability. Of course, DNS4EU doesn't today support actually checking those signatures, but if such a signature encountered, at least there is no confusion about it. Yeah, so we have a blog article about this if anyone is interested in details. And otherwise, I think there's maybe some time for questions, or at the end, I don't know. I also don't see the chat right now, so I'll give it back to Magda.
Okay, great. Peter, thanks a lot for your great presentation. It's great to see the outcomes of your hard work. There are currently no questions related to your speech. However, I think that we are all simply just impressed by the facts. However, still feel free to write your questions either for Viliam or Michal or Peter. They are still here with us, happy to answer your questions. So now, the last but not least, I would like to welcome Mr. Viliam Peli. He is a research software engineer at CERT, and he will guide us through the DOS protection. Just so that you know who will be talking to you. He is very experienced in what he's doing. Actually, over 8 years of experience in developing resolvers, with the not resolver being a central focus of his career. And he has been contributing to NextOS for more than 10 years. So really great expert, and I'm very happy to have you here, Vladimir, and I'm curious on your presentation. So if you are ready and there are no technical issues, feel free to share your slides and tell us about your outcome. Great. We can see your presentation, so it works perfectly.
Oh, okay. Hello. So I'll be continuing in these more technical topics. Not resolver is at the core of the DNS4EU service, basically around the topics that Peter was talking about, and I'll focus on denial of service attacks and protection against them. So far in the not resolver, we did not have good facilities against this, like rate limiting or something similar. So that's what we are focusing on this year as part of DNS4EU work. This protections like rate limiting can be done outside the resolver itself, but having the ability to do it inside is better in some respects. One aspect is configuration. Perhaps it's often easier to have it inside in one piece than on multiple places. And another thing is that only the resolver really sees into encrypted communication, so it gives a better ability to understand what is happening and to control what is happening in those encrypted streams. Better than when you do this on some firewall or other place. Denial of service attacks are mainly relevant in public resolvers, which is like not our main use case. It's relatively rare to run something like that. So as you've heard, DNS4EU will be running an instance next year, I believe. And CZNIC is already running for many years based on not resolver 2. What I'll be talking about, the rate limiting is also applied the new code to our authoritative servers, but that's not really relevant here. It's just some things are shared because they are similar. And one significant topic that we focused on are amplification attacks that Peter mentioned a while ago. So I'll just quickly say it's for UDP communication. There the source IP can be forged, and very often such packets can pass through the internet. So that's one important part of that. And so the attacker can choose where the answer will come. And in case of DNS, the queries can be very small, just a few dozen bytes, contrary to answers, which can be relatively large. So there's this amplification effect. And the attacker can send lots of packets to multiple UDP servers or DNS servers in particular, and focus the amplified streams all to some victim machine or network, and that can be overwhelmed just by the amount of traffic itself. And there are a few restrictions that combat it. As Peter mentioned, nowadays the reply size tends to be limited. It used to be like 4 kilobytes limit, but in the past few years, DNS vendors cut this down so that it fits into a single packet. Though here I see it as a side effect because the motivation was mainly to avoid UDP fragmentation, which has some other unpleasant problems, like not passing through the internet too well or being easier to attack by for cache poisoning. Anyway, that's not a new thing, and it's very easy to restrict the UDP reply size limit. What we focused on now is adding rate limiting capabilities. In DNS, we have an option to use truncated answers. Those are, in this case, the truncated answers would be really minimal, the same size as the corresponding request. So that would kind of mitigate the amplification effect, and the truncated answer contains an instruction to the query that they should retry over TCP, so that they would not, they could continue the resolution normally. I believe all sane clients will do that. It will just take a little more time for the round trips, but otherwise it shouldn't be a big issue. But for a really large flow of traffic, we would of course ignore some queries and not reply at all. So that's one area that we focus on, and that's for UDP. For non-UDP traffic, we choose kind of less usual strategy. There we see the main risk is overloading CPU. So if too much work is coming for the resolvers, it's not possible to answer everything because the CPUs aren't powerful enough at some point. And what we want to do is to choose what gets answered. So we want to prioritize some clients and answer those queries immediately. Say we have someone important on a whitelist, that could be so, or it's clients that send very little traffic, so we don't want them to feel any kind of attacks if someone else is sending too much traffic. So we kind of differ a resolution of some more expensive clients and maybe not manage to catch them. So now I'll just look a bit deeper into those two topics. So for rate limiting, you can for start imagine that for a user we store some count of requests, and when a request comes, we will if the user is not over limit, we just simply increment the count. Otherwise, we restrict the answer. And that way we track how much they ask, and over time we want the counts to go down as well. So each millisecond we multiply it by some constant, and so it will, over time, when if no more requests come, it will go down by some steps. And this is controlled by two configuration parameters. Here's an instant limit. So if a user wasn't sending anything for a long time and it starts at 0, at a single moment, they can send up to this instant limit of requests. And then the size of this step down from the maximum value, that's our long-term rate limit. Because after 1 millisecond, the value jumps this down, so that's exactly the number that they can utilize again. And this gives us some exponential decrease. That's really more of a detail. As I see it, by controlling the ratio of these two limits, you can control how fast these counters react. So how fast they forget that you had a lot of traffic. So this graph was when no more requests come. So that's not really usual. If there's a constant stream of requests incoming, it looks more like this when we are under limit. In case the requests are coming over the long-term limit, eventually we get on the ceiling here and start in the red. We start restricting a part of the answers. So we still answer as much as the rate limit, as much as is configured. And of course, it's possible to send a very fast traffic and get rate limited even in the first millisecond over the instant limit even. So that's how the counters work. And so far I simplified this and said that we are limiting some user, but what we see really are IP addresses. And it's not practically possible to just look at individual IP addresses and limit at that level only, because especially for IPv6, you can have basically an infinite number of different IP addresses going to a single machine or a very small network. So you can rate limit just on that level. What is usually done is that the vendor chooses some length of prefix, like first 24 bits of IPv4 addresses, and rate limit on that level. We instead choose to limit on multiple level at once. We found that it's actually the implementation low level of the tables and such stuff is very efficient, so we can afford to do many layers at once, even in authoritative servers, which are more performant. And so how it works is that it's similar to the slide before. So when a request comes, so we see an IP address, we apply a set of prefix lengths and look at the counters. If all counters are under the limit, we increment all of them. If at some layer it shoots over, we instead just restrict the answer. For this, there is kind of alchemy to choose the prefix lengths. We try to inspect how IP addresses are allocated in practice, and to choose some suitable prefix lengths and the associated multiplicators of limit. Yeah, well, what is important here that the limits on larger networks are higher, of course. So here, like /24 in IPv4 has 32 times higher limit than a single IPv4 address in this case, and that is. I mean, this multi-level approach has an advantage that when a single machine, a single IP address gets loose and sends too much, it won't expand the whole limit of some larger network. So the other neighboring computers could still be completely unaffected by this event. So yes, setting this this constants is really up to future changes, I think, because it's really unclear how to exactly choose. But okay, that's the scheme here. So that was the rate limiting part, how we design this, and the other bigger topic here is prioritization of work. So the rate limiting is mainly focused on the reflection attacks. So there we care about where we send the answer, because it might not be even the user who asked. In case of non-UDP transports, we have the kind of luxury that we know that this spoofing of source IP address can be done, and at least not in this sense of reflection attacks. So here we chose a different approach. And so when we focus on protecting against exhaustion of CPU power, it's important to know that for resolvers, there is a very large variability in how expensive it is to answer one request. In practice, most requests, a vast majority of requests are answered completely from cache, and therefore they are quite cheap. However, there are still many legitimate cases where answering the request is an order of magnitude more expensive than that. The resolver may need to ask several authoritative requests, jump over some CNAME chains, validate multiple DNS signatures, etc. They may be lots of work, and therefore it does not suffice to measure just the count of requests, because attackers could choose more expensive requests and they would get a large advantage over normal traffic. Fortunately, we found out that it's relatively cheap and easy to measure how much CPU time we expend on each request. At least we tested it on normal x86 Linux systems, and the overhead is really small. So that's what we do. We measure how much the requests take, and we can account it to the one who queries, who caused the work. The user asking this. In this case, we even know that the source IP address is real, that we really account to the attacker and not to the victim's IP address that was substituted by an attacker. And we are using exactly the same scheme with counters in tables as I explained in rate limiting. So we have these multiple layers for networks. We accumulate the time that we spend and we decay it over time. And so when more requests come, we know how expensive that user has been recently, and that allows us to choose if we answer that request immediately or if we just delay it until we have no more work that has a higher priority. And of course, it may happen that if we have too much to do, some of those requests will fall out we won't keep them more than a few seconds because no one really waits for answer too long anyway. And so, yes, that is the scheme for prioritization. So yeah, the main, I should stress the main focus of this was so that good users that don't overload the service are not impacted by any attacks, or be it intentional or unintentional. They get their answers immediately and reliably. Okay, so I believe I've described it all. These two groups of our focus for denial of service protection this year. I'll be happy to answer questions.
Okay, great. Thanks a lot, Vladimir, for sharing your work and your data. There are currently no questions for you. However, if there are any questions in the future, feel free to reach out to either to the speakers or to me. I believe that we've covered pretty much all the questions, and I would like to thank you all for attending, for sharing your thoughts with us, for the discussions that we have. It was very insightful, and I hope that it was valuable and insightful for you as well. And also, I would like to thank very much to our 4 speakers that joined me today and share their expertise with us. And if there are any questions, just feel free to reach out to either me or to contact at joindns4.eu, and we will be happy to answer all your questions. I will send the feedback form to all of you to see if this conference met your needs and if you were satisfied with the content. And I will also share the slides and the recording with you all. So once again, thanks a lot for joining us today, and see you next time during a different event.
Thank you, Magda. It's been a pleasure.
Thank you, Magda.
Bye.